Yeah, hi everybody. My name is Rich. I am a junior from Clements High School. And today, as part of the YEA Big activities, I'll be giving you all a lecture over a topic in computer science that I think is pretty interesting and that I've actually recently discovered, which is called suffix trees. Now, let me just share my screen so that I can get started with the presentation. Here we go. And of course, if at any time anybody has any comments, questions, or concerns, then feel free to go into the chat and you can either direct message me, say your question out loud as there are not that many people, or you can put your answer or question into the chat and I will get back to you as soon as you can. But since there do not seem to be any initial questions, let's get started. So the first thing I want to quickly go over is a question from the 2017 USACO December contest, which I think is sort of and I think just this question is a really good introduction into understanding how suffix trees can be extremely important. So I want all of you to quickly read through this not very long question for say 2 to 3 minutes, just so you can understand what's going on and perhaps think of a few ideas that you might have as to how to solve the problem. So I think we can regroup back here at around 7:06. All right, so it is now 7:06. So let's quickly discuss a few interesting things about this problem. So the first thing that we can sort of notice is that we want to count the number of unique substrings inside each cow's name. So for example, in the sample case, we can see that we have the cows Amy, Tommy, and Bessie. And now what we want to do is we want to take a look at the list of the substrings for every single one of these cows. So as you can see, the substrings for the sample cases are listed up here, or at least for Amy and Tommy. And now what we want to do is we want to count exactly how many substrings each cow has, such that these substrings are not included in any other cow's list of substrings. So example, for Amy, we can see that her list of substrings would be A, M, Y, AM, MY, and AMY. The reason that things such as, for example, AY are not included is because a substring must consist of consecutive letters. So I guess just sort of on an off note, we can notice that the number of substrings for a cow with n letters is going to be n times n plus 1 over 2. Now, let's look at which one of these substrings are not included in any of the other cows. So for example, we can see that A, no other cow includes an A, so this one works. For M, we can see that Tommy has an M in his name, so M is not unique. For Y, similarly, there's a Y in Tommy. For AM, because there's no A in any other cow, this is unique. MY, we can see that Tommy has MY at the end of his name, so this is not unique. And lastly, for AMY, we can see pretty clearly that no other cow has AMY in his or her name, so this is also included. So as a result, the uniqueness factor for Amy is going to be 3. Now, we can similarly get that the uniqueness factor for Tommy in this case will be 11, and the uniqueness factor for Bessie here is going to be 19. And just sort of doing out this sample case gives us an idea for how we're going to approach the problem. Because as for Amy, instead of directly counting out which one of these works, what we did is we took a look at the list of all possible substrings, and then we subtracted off the ones that we found were matching in some other list of substrings for the cows. So yeah, that's sort of going to be what our strategy is going to be for this problem. Now, the only issue is that finding which substrings appear in other cows' names is kind of hard, especially because if we notice that the size of the list of substrings for a name of size n, so for example, Amy's name is 3 letters long, the size is going to be 3 times 4 over 2. But since the total length of names is around 10 to the 5, this means that we could potentially be ending up with like 10 to the 5 times 10 to the 5 plus 1 over 2 names in a list of substrings. And this is sort of a lot of substrings that we're going to have to compare. And definitely not within the time limit if we're going to be comparing like every single individual set of 2 substrings. So now, this is where the use of suffix arrays is going to come in. So, but before I get ahead of myself, we should first answer the question, what is a suffix array? So just as sort of explaining what's going to happen, I'm going to quickly explain how a suffix array works, what exactly it does, and then we'll get back to its application to the problem. So this is sort of like the main part of the lecture, where we explain exactly how like suffix arrays are created and why they're efficient. So as you might be able to see from this diagram, what a suffix array does is it takes all the suffixes of a string and it sorts them in alphabetical order. So in the example for camel, we can see that camel, the substrings are C-A-M-E-L, A-M-E-L, M-E-L, E-L, and L. And when we sort them in alphabetical order, we get this order over here. So how can we do this efficiently, I guess? Now, the naive approach would be to consider each of these suffixes as separate strings. So for example, camel, amel, mel, el, and l. And then we can perform a sorting algorithm on this, just your normal arrays.sort. Or if you use C++, you can just use, I think it's like sort, and then like camel.begin, camel.end, or something like that. And but unfortunately, since we are sorting strings, each individual comparison takes O n time. And since we have to perform O n log n checks, then we have to multiply by O of n log n, resulting in a total runtime of O n squared log n to sort all of these strings, because it takes O of n to compare 2 strings. And generally, O n squared log n is not a runtime that we're going to be looking for, especially when there might be like 10 to the 5 total characters inside of the array. So there is a certain construction of these suffix arrays that allows us to construct the entire subarray in O of O of n log n time. And yeah. Okay, let's move on to the next slide. Oh, that didn't work. What? There we go. Yeah. So sometimes we want to be able to quickly obtain an array of all the suffixes and sort them in increasing order. But as I explained previously, we can't just use arrays.sort or sort arrays.begin, arrays.end, because comparing strings takes O of n time. So as a result, we must instead continually, we can use like a different strategy of continually comparing the prefixes of length 2 to the I for all strings, and then using the ordering obtained from the prefixes of length 2 to the I minus 1 to perform each iteration in O of n time. And since the step is going from 2 to the I minus 1 to 2 to the I, and this takes O of n log n total. Now, I understand that at the moment, it might seem like, oh, okay, so I might understand this first bullet point, and I might understand the second bullet point, but this third bullet point is just like, what is going on here? And don't worry, because we're going to go through an example, which is probably going to be a lot more instructive than just reading whatever gibberish is written here, which might be pretty difficult to understand if you don't know exactly how the efficient construction of a suffix tree works. So let's quickly go over exactly how this is going to work now. Okay, so let's think of some suffix that we want to sort. For example, like, let's say we want to sort the suffixes of the string banana. So B-A-N-A-N-A. Now, as I mentioned before, the main part of sorting with these suffix arrays is going to somehow being able to like do some step of 2 to the I minus 1 to 2 to the I, which should somehow allow us to construct the tree in log 2 n time, which is a lot more efficient than n squared. Now, how is this going to work? Well, this is exactly what's going to happen. So we look at the string that we have, which in this case is banana, and we do the following. So we start out by looking at each individual substring. So we have banana, nana, nana, A-N-A, N-A, and A. Okay, that was written very sideways, but I think it still gets the job done. And we're going to assign sort of a ranking to each number depending on its first, its first character. So for example, we can see that banana starts with a B, so we can assign a rating of 2. And a nana starts with an A, so we can assign it a rating of 1. Nana starts with N, so we can assign it a rating of A, B, C, D, E, F. 14. Anna starts with an A, so we can also assign this a rating of 1. NA starts with N, so we can assign this a rating of 14. And A starts with A, so we can just assign this a rating of 1. So from here, we can now sort these numbers based on the number that we've assigned them. So in this case, after sorting, it would become a Nana at the top with a rating of 1. Anna, oh wait, okay, this is not actually, okay, sure, I guess we can have it like this one. Anna with a rating of 1, A with a rating of 1, banana with a rating of 2, NA with a rating of 14, and NA with a rating of 14. Now, something you might notice is that all we've done so far is sort it based on increasing alpha based on the first letter, right? We haven't actually strictly sorted it in alphabetical order. Because notice that although all the A's are in the beginning, then the B's and then the N's, like for example, it's pretty clear that A is going to be the first substring that's going to be first in the list of orderings for alphabetical because A comes before Anna in the dictionary. But in what we have currently, this is not true. So we're going to have to somehow sort each of these pieces within their individual blocks. So like within these 3 that are labeled 1, we're going to have to sort them to be in the correct alphabetical order. Within these ones that are labeled like B, we have to sort them. Obviously there's 1, but just consider it a block still. And within the ones that we've written NA, NA, and NA, we have to sort them within here too. So now, what we've done so far, So what we've done so far is we've sorted the numbers based on their first letter. So let's write that here. So this is like sort of their first step. So we've sorted based on the first letter. And we can store the orderings based on the first letter in some array, say temp. So let's just say that for now, temp stores the exact ordering of how everything works within the first letter. So as I mentioned before, what we're going to be doing is we're going to be sorting from 2 to the first 2 to the I minus 1 letters to the 2 to the I. So exactly how is this going to come into play? Well, we've sorted by the first letter, so that's 2 to the 0. So now let's sort by the first 2 letters, 2 to the 1. So when we sort by the second letter, we can see that, well, first of all, not every single one of these letters is going to have a second letter. Like A is not going to have a second letter, N is not going to have a second letter. Oh, no, sorry. It's just A that won't have a second letter in this case. But it doesn't really matter because for dictionary purposes, we can just assume that A has like some letter after it that precedes every single other letter of the alphabet. That's not much of a concern. But the concern is sort of how we're going to write the transition step. So for the second letter, what we cannot really do, as much as it might be tempting to just say, oh, okay, well, let's just now order them based on the second letter, like N, A, and then order within blah, 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 blah. But this is going to be too slow because, for example, upon reaching this transition state, like let's say that we had 1,024 letters. In this case, if we were going like the transition state from 256 letters to 512 letters, then this would be like really messy. And yeah. So instead, what we're going to do is we're going to use the results that we obtained from the first letter and use these to sort by the second letter. So notice that right now, our prefixes are sorted as follows. So we have like A, N, A, N, A, N, A, B, N, A, N, A, N, A, blah, 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 blah. Now, in order to sort them by the first 2 letters, we sort of already have them split into these individual blocks. All we need to do is to sort them within these blocks. And here, the letters that matter are going to be the second letter. So in the first block, it's this letter that matters, and well, this doesn't have a next letter. In the second block, it's this letter that matters, and in the third block, it's this letter that matters and this letter that matters. However, because we've technically already sorted all the prefixes by their first letter, notice that the second letter of A, N, A, so second letter of A, N, A, is the exact same as the first letter of N, A. Meanwhile, if we look at A, N, A, then the second letter of A, N, A is the same as the first letter of N, A. And I mean, we can keep doing this for like every single letter, right? Obviously, except this one because it doesn't have a second letter. But the second letter of banana is just going to be the first letter of banana. The second letter of nana is the first letter of Anna. And the second letter of na is just A. So we see that we now have all these second letters, right? And they're all equivalent to the first letter of some other term in this sequence. And these are the first letters of the sequence that we've already sorted. So we already know the ordering of these second letters. Because if you recall, we stored all of the orderings of the first letters in temp. So now using our information in temp, we can sort within, right? So let's look exactly how this would work. So within the first block, we start off with A, N, A. And so we can see that during our first ordering, the second letter of Anana, which is Nana. So the first letter of Nana had an ordering of 14. So within the block, we can say that Anana now has a size of 14, let's say. Then we can say that the next one, which is ANA, or an ANA, since the second letter is also N, or since the string not including the first letter is just NA, and the first letter of this is N, as we can see here, then we can say that this also has a size of 14. Meanwhile, A doesn't have a second letter, so we can just say that this has a size of -1, which basically means that it's smaller than everything. So these are our sizes for the second block. For the third block, which is banana, since we're trying to sort by the second letter now, we look at the string here after the B, which is anana, and we can see that anana has a size of 1 when we sorted by first letter. So here we'll say that has a size of 1. For nana, we can see that when we sorted by first letter, Anna had a size of 1. So this is also granted a size of 1. And lastly, NA, which had for NA, if we look at its last letter, which is just A, we can see that A had a size of 1 when we sorted by first letter. So this is just 1. So as a result, now we sort of have new rankings for each of these inside each individual block. And in order to just complete the step of sorting everything by second letter, all we have to do is sort each one inside its individual block. So now the new ranking should become like A, N, A, N, A, N, A. Here is still just banana. This is still nana and NA because the ones are indistinguishable. So you can now see these as our new blocks. And the main thing to notice here is that the A has been separated from anana and Anna because it had a -1 here instead of 14s, which is what is matched here. So you might be able to sort of see the gist of how exactly this is going to work now. So we're going to keep on using the results from the previous step in order to continually separate each of these into blocks until they're all separated into their own blocks, at which point we know that the sequence must have been sorted alphabetically. So let's quickly see how the sorting would finish. So we've done the second letter, so now let's do the fourth letter. Because as you recall, we're going from 2 to the I minus 1 to 2 to the I. So let's see, right? All right. So A, so if we look at A, we can see that this obviously doesn't have any letters past 2. So we can just assign this a roll of -1 again. Looking at anana, we can see that the last 4 letters, or like past the first 2 letters, is just going to be Anna. So since when we sorted by second letter, Anna had a size of 14, then we're just going to give it 14. All right. Now looking at Anna, or just ANA, looking past the second letter is just the string of A, and A had a size of -1, so we can assign this a size of -1. Similarly, if we look at banana, looking past the first 2 letters, we obtain a string of nana. Wait, banana, yeah. And nana has a size of 1, so we can give this a size of 1. And we can just do the exact same thing for these 2. I won't bother like reading it out, but just know that it looks like this. And at this point, if we group them within their individual blocks, we can see that everything should be sorted. -1 is less than 14, so Anna is moved above Anana. So now our ordering just becomes this. And similarly, because NA had a score of -1 in this case, whereas Nana had a score of 1, NA is moved above Nana. And since now during this, cycle, none of the suffixes that were in a block with another suffix ended up receiving the same score. So for example, in the second block, we see that we receive scores of 14 and -1, which are not the same. And in the fourth block, we receive scores of 1 and -1, which are also not the same. Then this means that each one of these suffixes must now be in their own block. So we know that the suffixes must be fully sorted. Okay, so that was a pretty long explanation as to how to use suffix arrays. So if anybody has any questions, then please feel free to ask, because we sort of did cover a lot of ground with just a very short explanation of one example. I will give people, like, even if there are no questions, I'll give people 2 to 3 minutes to see if they have any sort of, if they want to still absorb the information, or if people are still trying to understand what's going on, which is a definite possibility. All right, so it does not seem as though anybody has any questions. So let's move on to the implementation of the code. Why can I not move on? This is very strange. Okay, there we go. So yeah, this is the version of the suffix array code that I have, I guess. I created this a bit ago, and it is sort of inspired off of some articles I read off of how to create suffix trees. So I guess you could say, while it's partially original, it's not like fully original. But yeah, so if you want to get a feel for exactly how the code works in suffix arrays, if you could just search up suffix array on Google, then you should be able to find like quite a few implementations of suffix arrays, that some of which have explanations, some of which don't. But you can read through these to sort of understand exactly how the code for the suffix array works. I remember that the ones I looked at were like Geeks for Geeks, and then CP Algorithms had an implementation. And then I think Algorithms for Help, I think is what it was called, also had an implementation. I looked at all of those to sort of see which one I liked the best. But in the end, this is like the version of the suffix array that I felt was most intuitive for me. I'm not sure if we'll have time to fully go through everything, but I will like sort of explain briefly how everything works. So let's see. So the first thing I did was construct a structure called suffix. Oh, and this is in C++, by the way, for those curious. So the first thing I did was construct a structure called suffix, and this holds the index, and this index is the original position of the number. So for example, if we recall in our previous example, for all of our suffixes, like banana would be index 0 because the first letter is B, which is the first letter. A nano would be index 1 because it starts at A, which is the first position of the array. And this is so that after you sort, you don't lose track of which suffix is in which position. Yeah. Now, the next part here, this comparator, compares two suffixes, suffix A and suffix B. And if you recall, back in our example, after every single step, like when we did sort by 1, sort by 2, sort by 4, we had to resort every single suffix within its individual block. And this is what this comparator does, in essence. So it's going to look inside every block. And if the size that we assigned to each suffix is different in this case, then it's going to rearrange them so that inside its block it's in order. And then afterwards, it will break the block for all of the numbers that were not the same, or for the sizes that we did not receive that were the same. So the comparator is just the after effect, or just what happens after we assign the sizes for every 2 to the I. Now, this function right here is the main part of the suffix array. So basically what you do is you give it a list of characters. And so for example, in our case, the list of characters would be like this, etc. Now, once you give it this list of characters, it will return to you the suffixes in alphabetical order, which is why it's returning vector suffix. So let's see. So what this code right here does is it starts off the 2 to the I iterations, starting off with 1. So as you can see here, the first thing that it does is it sorts these suffixes based on their first character and then groups them into blocks. The reason that suffix has rank 2 here is so that so rank 0 is going to hold which elements belong to which blocks, and then rank 1 is going to hold the size. So I guess if you recall, inside each of our when we were sorting, we had different blocks of elements. So for example, maybe we had Anna, A here, and then we had Nana here, for example, where these were in the same block and this was in its own block. And then we were assigning sizes to each of them too, something like this, right? So what rank 1 is going to do, or sorry, what rank 0 does is it identifies which of these blocks the suffix is in. So for Anna, rank 0 would be 0. For A, rank 0 would also be 0. But for Nana, rank 0 would be 1 because it's in a separate block from the other two suffixes. While rank 1 is going to be the size of the new iteration. So rank 1 for Anna would be 14. Rank 1 for A would be -1. And rank 1 for Nana would be 14. So that's sort of what rank does here. And this just sets up the initial part by ranking everything into its initial blocks based on the first number. All right. So where the bulk of the work happens is inside of this for loop. And this for loop is the thing that's iterating that causes us to go from sorting from the first 2 to the I words into the next 2 to the I plus 1 words, which you can see is why we're multiplying I by 2. So what this code does here is so what this code here does is this is how we all right, this code here rearranges everything into blocks. So if you recall, we had to rearrange things into blocks based upon whether their size here was the same on the previous iteration. And this code's pretty long, I guess, compared to the stuff below it, but it gets the work done. While the code here is what assigns us the new sizes. So for example, when we were comparing the last two strings, if we were looking at this, then this code right here is going to get us the size of NA in the previous iteration of what we ran and assign the size to the substring based upon the previous size that was obtained. And yeah, I think that's a pretty brief run through of how exactly the suffix everything works. Obviously, you could still probably have some questions about how some of the parts work. So I highly encourage you to search up suffix trees online, or sorry, suffix arrays online, so you can sort of get a better feel for how exactly to code this should it pop up in your contests. Oh, and I guess one final note, the reason that this is O of n is because, So obviously everything before this is constant runtime, or this is ON, but it doesn't really matter. Where this, so this for loop is O log n runtime, because we go from 2 multiplying by 2 up to n, whereas this for loop right here is also ON. This for loop, these two for loops are both ON. So as a result, oh, and comparing is comparing is constant runtime. So as a result, the only thing we need to check is how fast this for loop is. And the outer for loop is O log n, and every single inner for loop is O of n. So the total runtime is going to be O of n log n, which is something that we definitely like to see in our coding contests. Anything with like n log n, n log squared n, all this stuff is very nice. All right. So now we have finally completed, or I guess we have finally figured out exactly what suffix arrays are. So now let's come back to the reason why we decided to discuss suffix arrays in the first place, which is solving the standing out from the herd problem with suffix arrays. So in case anybody needs a brief refresher for what the problem statement was, let me go back to the problem statement. It is this. And I think that I will sort of go over how to use suffix arrays on this slide so that if you all want, you can look at the question in case you sort of forget about what it's asking, or if you just want to like test things with the sample case, you know, that sort of stuff. All right. Now, sort of, this is just what we're going to do, right? So the first thing we're going to do is take each of these strings and put them into one long string, separated by some separating thing, like we could say question marks, could separate the individual names. So for example, the names could be like Amy, then we put a question mark to show that there's a new name, then Tommy, then we put a question mark to signal a new name, and then Bessie. And then I guess still a question mark because that's how a for loop's run. So we have something like this. Now, using the idea that we need to construct a suffix array, we're going to construct a suffix array. So let's call it like this, for example. I guess we can just call it suffix SA for suffix array. We build a suffix array of this string, So this suffix array is going to hold like everything here that's all the substrings of this sorted in alphabetical order. Now you might be wondering, well, what about the suffixes with the question marks? Well, the reason that we added them with question marks is because question marks come before any ASCII characters inside of the, question marks come before lowercase letters in ASCII. So as a result, all the suffixes with the question marks will come at the very beginning of the suffix array. So this means that we can just sort of ignore them in whatever way you want. You can like start at the index right after the question marks, or you can just remove them from the array altogether. It's really up to you what you want to do. So yeah, so SA now stores the suffix array of every single one of these. But you might be wondering, like, well, isn't that useless? Because we don't have the suffixes of every individual cow. Like the suffix starting from M is going to be like MY with all these extra characters at the end because we concatenated it into one string. Like this is not just the substring of MY. This includes all the junk that comes at the end as well. And yeah, this is true. But we can, like using some code, I guess, we can pretty easily determine exactly how many characters are in the relevant part of the suffix or in the part of the suffix until they hit a question mark. So for example, for each of the substrings, like even for Tommy, like this part, we can pretty easily run a loop to determine exactly how many characters there are in the suffix until we hit a question mark. And it's at that point that we know that, oh, this is the number of characters in like this specific cow's name that are not up to like the end of his name. So we could say, oh, MMY is the number of characters that are relevant here, which is 3. And MY is the number of characters which is relevant here, which is 2. So we sort of just created a suffix array, yeah. Now, the way we're going to use this is as follows. So we claim that if we run a loop through every single suffix in our array, so we loop through every suffix in our array, And we keep track of the following things. The first thing we keep track of is the suffix right before Okay, and I guess we could like just call the one that we're currently on I. So let's say the first one's I, right? We keep track of the suffix right before I and the suffix after I that is not in the same name. And what I mean by this is, for example, for this suffix right here, we can see that this suffix, it starts off in the name Amy. So a suffix that comes after it that is not in the same name group means that the suffix should not the suffix should not have its starting point inside the name of Amy. It should start in either Tommy or Bessie. All right, so now why does this work? Well, the reason that this is enough to solve the problem is because the suffix right before, so I guess first considering the suffix after I that is not in the same group as the suffix that we've chosen. So for this one, we have so for this one, so based on the way we've constructed the suffix array, we know that either the suffix right before or right after the suffix that we've currently chosen is going to share the max amount of letters with our current suffix. However, and normally this would be enough. Like we could just consider the left suffix and the right suffix. So like in our suffix array, let's look at SA, right? We're going to have like suffix 1, suffix 2, suffix 3. And based on the way we've constructed this, like this suffix is going to share the most letters with either this suffix or this suffix. And like this suffix is going to share the most letters with either this suffix or this suffix. And so basically it's enough for each individual suffix to sort of look at these two suffixes, see which one it shares the most letters with, and then subtract off that many from this suffix saying like, oh, okay, so let's say that it shares 6 with this one and then 5 with this one. The maximum it shares is 6. So that means that this suffix is going to be relevant for its length minus 6 because that's how many characters it shares. And we can do that for every single one. So normally this would suffice, but the reason that the leftmost one does not have to come, the reason that the leftmost one can be in the same one is because we want to avoid overcounting the suffixes that are in the same. So for example, if we remember in Tommy, there's 2 M's, right? There's an M here and an M here. So by only subtracting when the suffix right before it is the same, we deal with this overcounting. So as a result, we can just loop through all suffixes I, find the maximum number of characters shared between one of these two, and then assign this subtraction to the proper name. And then after that, the problem becomes pretty easy. And yeah, I understand that I kind of rushed the ending of it, but I do apologize because I do have to get going like very soon. So if anybody has any final questions for me, then I would be happy to take them in the next like minute or so. Yeah, sorry for the sudden interruption, I suppose. Okay, well, it does not appear as though anybody has any, I guess, questions for me. So let me just skip to the end. Yeah, so I guess that's going to be the end of our presentation for today. Hopefully you guys all learned a bit about suffix arrays. Again, I understand that the end was short, like cut short a little bit. So I highly encourage you all to sort of, you can go to USACO and read the solution for this problem, or just go to like another website and read up more on suffix arrays if you thought that these were really interesting. And yeah, thank you so much to YEA Big for allowing me to sort of have this really fun presentation for all of you guys. And I wish you guys all luck in your future coding careers. Thanks so much to everybody for coming. I will see you guys later.